All right, welcome back to Trail Math. And this time it's the cool guy doing it because I have these sunglasses on.
What the heck?
Hectogon.
So if you saw my short from a few days ago, you'll remember I asked a bit of a tricky geometry question. I asked, can you triangulate a square, as in slice it up into triangles, where all of those triangles are acute? Someone claimed in the comments that they were able to do it with 6 triangles, and boy have I got some bad news for you today. Well, here's my example with 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And we're going to be walking through how you can prove that you can't do below a certain number, and we're going to show that you can do any number above that. The little foresty transitions between scenes, not going to be so jarring this time, I promise. How are we going to tackle this problem? Well, first we sort of got to figure out, all right, bye Gus. First we got to figure out what's going on here, right? Let's make some observations. So what I'm going to do is I'm going to erase the question in question. Et voila. So there's different kinds of vertices to these triangles that we need to consider. Let me just finish my square there. Not quite completing the square that you remember learning. The triangles have to exist somewhere in here, right? Of course. And there's multiple things we need to observe. For example, the corners of the square are right angles. So right off the bat, we cannot let them stay the way they are, or else the triangles that we have in here are not going to be acute. So at the very least, there needs to be the edge of a triangle, at least one edge of a triangle coming out of every corner of the square, okay? So that is something we need to make sure is going to happen. So right there, we need at least that. We might also have the corner of a triangle right on the edge of the square. Well, the entire angle that you have here is 180 degrees, right? If we sort of imagine pointing this way and then pointing the other way, it's 180 degrees. So to turn this into acute triangles, at best, we need at least at least 2 edges coming out of that point. That way, these 3 angles that we form there are all acute. So they have to obviously not form any right angles or any obtuse angles, so there needs to be at least 3 coming out of any point on the edge. And if there is a point inside the square, there needs to be at least 5 edges coming out of it. Otherwise, if you have only 4 edges coming out, you're guaranteed to get at least 1 right or obtuse angle out of that. Except if you end up with something like this, where you have the edge of a triangle and then a point on the edge of that triangle. So imagine there's a triangle over here, a point on the edge of that triangle. Well, this behaves precisely like a point on the border of the square. So you only need 2 or more coming out of one side if if this part over here is like the inside of a triangle. So this point is not on the corner of the triangle, it's on the edge of another triangle. So those are our different options. We either have corner points in the square, border points on the square, or internal points in the square. And so the next stop we're going to do is we're going to take a look at how we might be able to take a shape that we have in the square and subdivide it into acute triangles. So now that we've made that observation, let's move along. There's no reason for me to wear these glasses. Before, we observed that you need a certain number of edges of the triangles coming out of particular places in the square. The next observation we should make is, can we take a shape we already know we have and subdivide it into acute triangles? So a very important example of that is if we have a right triangle or an obtuse triangle, we're always able to break these up into 7 acute triangles. We shave off the tips of the triangles there, so those 2 triangles are acute. And now in the middle we have a pentagon, and we can always put a dot in the center of a pentagon and break it up into 5 acute triangles just like that. So I've taken an obtuse triangle and I've broken it up into 7 acute triangles. And the exact same thing can be done with a right triangle if you have a little bit of care in placement. And you put the dot there, and hopefully if I've done it correctly, That should be less than a right angle. It might look like it's about a right angle, but let's just pretend that it's not, because I assure you, you can do this. So what we've done here is we've shown that we can take a right or an obtuse triangle and break it up into 7 acute triangles. Now, why is that important? Well, this is how I constructed the 14 example that you saw at the beginning of the video. Let me show you what I mean. How can I use that subdivision trick to turn this into 14 acute triangles? Well, I can quite simply draw a diagonal, and now I have 2 right triangles which I can subdivide in the way that I showed you. So I end up with 2 acute triangles like that, put a dot conveniently there, and break this up into 5 acute triangles. So those angles there will be very close to 90, but they are in fact less. And I can do the exact same thing with this right triangle up here. It's going to look a little bit off, but I assure you, you can do this construction. It does work. So it does look a little bit more, it does look a little obtuse there, but pretend that it's not. You definitely can do it. You just got to be very careful with where you put the point. And you'll notice there are 14 triangles here. Now, the example that I showed you at the beginning was slightly skewed from this, just to hide the fact that this is what was really going on. So it turns out then, from here, we can figure out how to construct everything more than 14. Because all we have to do is simply add as many acute triangles as we need, and then do these 2 decompositions here. I'm going to put a big acute triangle right in the middle, like this. Right, that's an acute triangle, and you'll notice what I'm left with here are 2 right triangles. So I can do the same decomposition that I just showed you, where I break them up into 7 acute triangles like that, and I do the same over here, that, and now I have a solution with 15 triangles. There's 14 and 15, and then the last thing I'll show you is how we can construct 16 from this, and I think you'll be able to see how the pattern continues. I'm going to put 2 acute triangles in the middle, and you'll notice I'm still left with 2 right triangles on the left and right, and I can go boop and boop, 5 acute triangles like that, and I can go boop and do it again. From here, if I wanted to do 16 right acute triangles, I'm sorry, this is 16 acute triangles. If I wanted to do 17, I would just have to put 3 large ones in the middle, and then I could do the same decomposition on the left and right. I could do 18, 19, 20, as many as I want. So this 7 triangle decomposition is just one of the ways that we can break up triangles, or break up shapes into acute triangles. The other way is if we actually have an acute triangle already. And you will have learned this in geometry class, that you can break up any acute triangle into 4 similar acute triangles by finding the midpoint of every side and connecting them together with their mid-segments like that. And these 4, you might call this the Triforce operation if you've played any Zelda. I think it's Zelda. Who knows? I never played it. So we can break up an acute triangle into 4 acute triangles just like this. So we've seen that we can turn a right and obtuse triangle into 7 acute triangles. And we've seen that we can take an acute triangle that we already have and turn it into 4. So we can increase the number of triangles by 3 if we already have a solution. That's pretty nice. And then the last decomposition I want to show you is if you have something like a trapezoid or something close to a trapezoid inside your square triangulation, and it looks like this, right? That's sort of like the bottom part of the Triforce thing. I can replace this middle triangle with 2 triangles like so. I can go boop, 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 boop. And so what we've done is we've turned a trapezoid with 3 acute triangles into a trapezoid with 1, 2, 3, 4, 5 acute triangles. And I can keep doing this. Every time I replace one of these really pointy ones with 2 pointy ones, my number of triangles goes up by 2. 1, 2, 3. And now I have 1, 2, 3, 4, 5, 6, 7 acute triangles in that trapezoid. So those are all the decompositions we're going to need to be able to prove that we can do everything above a certain number. So the next thing is going to be to prove what we cannot do. So we've shown that we can do 14 and above. We've seen how we can subdivide shapes into acute triangles, and we've seen how many edges have to meet at certain points. So that last thing I just said, we're now going to explore the algebra of that and see if we can maybe prove what the minimum number of triangles we can have is. Let's say n is our number of triangles. We'll say that b is the number of border points. So border points being the ones that are on the edge of the square that need at least 2 edges coming out of them. And we'll say that I, not the square root of -1, but the number of internal points. I is the number of internal points, the ones that need at least 5 coming out of them. B is the number of border points that need at least 3 lines coming out of them. And we know how many corner points there are, right? There's the 4 corners of the square, so we don't need to assign any variables to that because there's always going to be 4. And n is the number of triangles. So now we're going to utilize these amounts to do some algebra. So let's think about it. How many vertices are there? Well, we don't know how many vertices there are because sometimes triangles will share the same vertex, right? If we have something like this, right, like that, right? These triangles, they're not acute, but the point is that these 2 triangles share those vertices. So we don't really want to double count them, but in this case, we actually do. So if there's n triangles, right, n triangles, however many there are in our square, let's imagine counting every single vertex for every single triangle. Well, each triangle has 3 vertices, so if we counted every vertex inside of each triangle, we would have 3 times n. Hopefully that seems reasonable, right? We count each vertex in each triangle, so however many triangles there are, we're going to get 3 times as much. And we know at every corner of the square, there must be at least 2 vertices tucked in there, right? If this was the corner of our square, there's got to be at least 1 triangle there and another triangle tucked in there. So this number has to be greater than or equal to 8, because they're going to have 2 triangles at each corner of the square, so that's where the 8 comes from. And then we know there has to be at least 3 triangles tucked into each border point, so we're going to have plus 3 times b. And we know there has to be at least 5 triangles tucked into each internal point, so plus 5 times I. So if we count every vertex, triple counting, you know, every single triangle, that number has to be at least 8 plus 3 times the number of border points plus 5 times the number of internal points. We need more information. What's another thing we can figure out about triangles? Well, we can talk about the total amount of angles inside of each triangle. We know that every triangle has 180 degrees of angle in them. So if we ask how many triangles we have n triangles. So the total angle inside of all the triangles is going to be 180 times n, where 180 is the number of degrees. And now what we can do is we can add up all the angles for all the vertices, right? So we've got the 4 right angle vertices here. So we know each of those is going to be 90 degrees, and there's 4 of them in total. I'm just pretending the board is my square. So that's going to be a total of 90 plus 90 plus 90 plus 90. That's 360 degrees. And then we know that at each of the border points, right, imagine like that, that's going to be a total of 180 degrees. So there are b total border points. So it's going to be 180 times b. That's the total amount of angles that each of the border points contributes. And we know that if we have a point inside the circle, all the parts that come sticking out of that, right, the total angle here is going to be a full 360 around that internal point. So each internal point contributes 360 degrees, so we must add 360 times I, the number of internal points. So we have a thing that relates n to b and I, and we have another thing that relates n to b and I. So what I'm going to do is erase this stuff up here, and we're going to put them inside one another. First thing we need to notice is that everything here is divisible by 180. So I can just cancel all the 180s there. Divide everything by 180, and we'll have a much simpler equation. So cancel 180 there, we just get n. What's 360 divided by 180? It's just 2. So this is 2 plus, okay, 180 divided by 180, that's just 1. So 180b just becomes b. And 360 times I divided by 180 just becomes 2 times I. So we actually have a nice formula for the number of triangles. It's 2 plus the number of border points plus 2 times the number of internal points. Kind of convenient. But since we have this representation for n, we can take it and plug it in there. If we do that, we're going to end up with 3 times n. That's 3 times all this stuff right here. So that's pretty easy to do. 3 times this is just going to be 6 plus 3b plus 6i. And we know that this has to be greater than or equal to 8 plus 3b plus 5i. Okay, cool. Well, we know that this is greater than or equal to this. We have a 3b on both sides of our inequality. We can just cancel that away. We have 8 on the bottom part and 6 on the top part, so we can subtract 6 from the top and bottom. So this just becomes 2, and this goes away, right? So all the 3b's are gone as well. And now we're left with 6i is greater than or equal to 2 plus 5i. But of course, I can subtract 5i's from both sides, and we're left with the result that I must be greater than or equal to 2. In other words, if you have a proper you have a proper triangulation in the square, it's guaranteed that you must have at least 2 of those internal points. So I has got to be at least 2. Okay.
I'm good.
Good? So we've just shown that if you have a triangulation of the square into acute triangles, then there must be at least 2 internal points. Since each internal point has at least 5 triangles coming out of it, and we know that those 2 internal points must be connected, we can actually now conclude the minimum number of triangles that we're allowed to have. So each of those 2 internal triangles will have 5 things coming off of them. We know that each internal point will have 5 triangles coming off of it, so 2 times 5, right? 2 internal points times 5 triangles. But then notice that these 2 internal points will share 2 triangles, which means counting this many is overcounting by 2 triangles, which means we need to take 2 away to get the minimum number of possible triangles, which is 8. You must have at least 8 triangles to triangulate the square with acute triangles. So the fella or lass that commented on my short saying they did it in 6, no you didn't. You didn't do it. It's not true. You've made a mistake somewhere. Somewhere there's an obtuse or a right angle, and you gotta try again. So in the next spot, we're going to see what the solution with 8 triangles is, and we're gonna see how we can create every other number of triangles. Let's do it. So what have we shown so far? We've shown that you must have at least 2 internal points to make a proper triangulation of the square. An acute triangulation of the square, I should say. And we know that we must have at least 8 triangles. Now that does not mean that 8 triangles is possible. It's just that you definitely cannot do less than 8. But it turns out 8 is possible. And it's very, very difficult to find if you don't know where to look. But it turns out it's incredibly sensitive to movements. It's like you know, moving the internal points around. So you have to be very careful where you place them. So it turns out you end up placing them quite close together right there. Connecting them like so. Like that. So there's 3 acute triangles. And then like that. And then we have a really tall and skinny acute triangle right there. And that, my friends, my lovely polygons, as I've for some reason taken to calling my small fan base, is the solution with 8 triangles. So there's 1, 2, 3, 4, 5, 6, 7, 8, all of them acute. You can see this is very close to being a right triangle here, very close to being a right triangle there. Moving these points around, you have a little bit of leeway, but not very much. Now, from here, since we have 2 trapezoids in our shape, one right here and one right here, we can do the subdivision that allows us to add 2 more triangles. So if I take this little triangle here and I break it up like so, we now have a solution with 10 triangles. So we've got a solution with 8, we've got a solution with 10, and now we can do the exact same thing with this bigger trapezoid in the middle here. We break up this triangle into much longer, skinnier ones like this. Not drawn very well, but I think you get the idea. And now we've added 2 more triangles, which means we're able to get a total of 12. So we've been able to construct one that's got 2 more than a multiple of 3 triangles, one that's got 1 more than a multiple of 3 triangles, and one that is a multiple of 3 triangles, which means we can now incorporate our subdividing an acute triangle into 4 acute triangles to add 3 to any of these amounts. Let me show you. So find the midpoints of one of the acute triangles like so. chopping it up into 4 similar copies, which means we've added 3 triangles to the total. And starting from any 3 of these numbers, you can add 3 to any of them, which means you can hit every number that's like 8. You can hit 8, 11, 14, 17, and so on. You can hit 10, 13, 16, 19, and so on. You can hit 12, 15, 18, 21, and so on. And that process misses only one amount of triangles, and that would be 9 triangles. So let's see if we can figure that out in the next part. All right, here's the last part as I kneel down in the snow next to our adorable mascot Gus here. And I want to show you how we can figure out the solution with 9 triangles. But first, the best way to do that is to sit down. Sit. Good boy. The best way to do that is to start with 10 in a way that I hadn't shown you before. So there's 3 acute triangles, and now we have an obtuse triangle down here. Can split that up in the way that we showed into 7 triangles, like so. And we now have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So another way to do 10. And this will be our inspiration for creating 9 by getting rid of this triangle right here. So let's do that. Hang on, sorry, I'm being stupid. There we go. And just like that, by getting rid of that little triangle in the bottom, we now have a solution with 9. Isn't that kind of cool? And of course, it's maybe a little fiddly over there, but you know, figure it out on your own. You'll notice that all of our solutions, except for the one with 8, always have these internal border points, right? It looks like a border point on the edge where we had to have at least 2 things coming out. And you see we sort of have the exact same thing there where 2 lines are coming out and it's along the edge of a triangle. Now, your task, my lovely fans, is to come up with a way to triangulate the square with however many number of triangles, but with none of these internal border points, you know, these weird ones that are on the edge of a triangle. Only these proper internal points are allowed. And of course, border points along the border. And the other puzzle is to prove that you cannot do that with 9. With every other one you can, and with every other one you can make it with the proper internal points, except for 9. And I think that's all. And goodbye.